Welcome to the physics seminar. Today we have Julia, is it Gehrlein, from Colorado State University. She is an assistant professor in their physics department. She's got interests in new physics scenarios. In particular, new physics around neutrinos and how we can use those to, make determinations of, what is the underlying physics that is governing really the universe. Like if we understand the neutrinos, then that's a window. I mean, the neutrinos are going to connect to a lot of different things across physics here. So it's quite interesting. She was a research fellow at CERN. I was also at CERN at one point, so that's cool. She was in the Brookhaven National Laboratory. She did her PhD at the Instituto de Física Teórica in Madrid. And then before that, you were at Karlsruhe Institute of Technology. So another, accidental overlap because I was at Karlsruhe for a little bit. It's all about me, by the way. But yeah, so on today's talk, she's going to talk about constraining new neutrino interactions with neutral current events. So I'm very happy to have her give the talk. So, and just kind of.
Yeah, I will click that. Right, so this should work, I think. Okay, great. So thank you very much. It's a pleasure to be here. So thanks a lot for the invitation. I already had some great discussions with people here. But yeah, today I'm going to talk about neutrino physics and how we can constrain new neutrino interactions using neutral current events at neutrino experiments. So we all know that neutrinos interact via the weak interaction in the standard model. But the question I want to pose is, are there any other interactions of neutrinos? And I'm going to talk about two different possibilities. One is about new neutrino fermion interactions. The other one is about a new neutrino standard model gauge boson interactions, in particular neutrino photon interactions. And I will show what we already know about these possible new neutrino interactions and then also talk about new constraints on them I've derived in my work. Okay, so in the standard model, we know that neutrinos interact via the weak interactions. So either they have charged current interactions mediated by the W boson, or neutral current interactions mediated by the Z boson. Both of these interaction strengths are governed by the Fermi constant. So it depends on the coupling strength of the weak interaction and the mass of the gauge boson. However, if we go beyond the standard model, if we consider the standard model as an effective field theory, then all of the operators up to mass dimension 4 are contained in the standard model, but operators of mass dimension 5 or higher can be parameterized in this effective field theory way. So the only higher dimensional operator we can build at dimension 5 out of standard model fields only. This is this Weinberg operator shown here, which couples 2 lepton doublets to 2 Higgs doublets, and it is suppressed by 1 high energy scale lambda here. And this operator, after electroweak symmetry breaking, gives mass to neutrinos, namely a Majorana mass. Going to dimension 6, we suddenly have way more operators. Among them are 4 fermion operators, including also neutrinos, and they can lead to new neutrino interactions, and the strength of these new interactions will depend on the Fermi constant of the new interaction. So it will depend on the coupling strength of the new interaction divided by this high energy scale, lambda. So new neutrino interactions with standard model fermions go under the name of neutrino non-standard interactions, or short NSI. There are 2 different classes of them: charged current NSI and neutral current NSI. Charged current, they're both parameterized in very similar ways as shown here. So charged current NSI relies on having a charged new mediator, neutral current NSI, you have a neutral mediator, and charge current NSI couples neutrinos and the corresponding charged lepton to different standard model fermions, whereas neutral current NSI, you couple two different neutrinos and to two different standard model fermions. The sums here go over different neutrino flavors, alpha and beta. The sum also goes over different standard model fermions F, as well as different Lorentz structures, P, so scalar, pseudoscalar, vector, axial vector, and tensor interactions. So there are lots of new physics operators involving neutrinos, which one can build. The strength of this new interaction is typically parameterized by this NSI parameter epsilon, which gives us the strength of the new interaction relative to the weak interaction. So epsilon is of the order of this new Fermi constant divided by the standard model Fermi constant. Since we are assuming that the NSI can be both flavor diagonal for neutrinos or flavor off diagonal, so alpha and beta can be different neutrino flavors. So there are strong constraints on charge current neutrino interactions. And here's an example. So generally, the strength of the interaction or this new high energy scale has to be above the TeV scale. And that's not surprising because these new interactions are really new charge current interactions of neutrinos involving the charged leptons, and we have very good measurements coming from charged lepton decays, but also meson decays via charge currents. So we have very strong constraints on charge current NSI. For this reason, I'm going to focus on neutral current NSI in the following. So again, it's parameterized in this way. We have many, many different operators if we take into account the different Lorentz structures. These operators can have the different flavor structures, alpha and beta, and the different standard model fermions to which the neutrinos can couple in this effective way. So there is lots of new physics to discover. So how do we probe NSI? And there are two main ways to do that, namely with neutrino oscillations and with neutrino scattering experiments. So via neutrino oscillations, we can probe neutral current NSI in the propagation of the neutrinos, as I will show in the following. We can also probe charge current NSI in the production of the neutrinos. Typically at neutrino oscillation experiments, the neutrinos are produced in meson decays or maybe in beta decays for reactor neutrinos. And then we detect them via charge current interactions. But as I will show, we also have a substantial amount of neutral current events at neutrino oscillation experiments, so we can constrain both charge current as well as neutral current NSI in the detection. There is no sensitivity to axial currents in the propagation of the neutrinos. We are only sensitive to vector and scalar NSI in the propagation of the neutrinos. Sensitivity to axial current in the propagation would require that we have a polarized medium. We only observe neutrino oscillations in the sun and in the earth. None of these materials are polarized to first approximation. As I will also show on the next slide, is that neutrino testing NSI in neutrino oscillations, we get constraints which are independent of the mass of the new mediator. There is no sensitivity to the individual diagonal NSI parameters, and there are some degeneracies. In neutrino scattering experiments, we do have a dependence on the mediator mass. We also need a theoretically well understood process because we want to compare our theory prediction to what we actually observe in the data. And if it's really, really hard to calculate our theory prediction, well, then we are not really sure if there is new physics in the scattering or not. We have observed a neutrino electron scattering, neutrino nucleus scattering in a couple of different experiments. So we do actually have a rich data set, but there are also degeneracies in the NSI parameter space. They are, however, different from the degeneracy in neutrino oscillations. So there is a nice complementarity between testing NSI in oscillations and in scatterings. So now let me show you two different examples of how we can test NSI in oscillations. I'm focusing on scalar NSI. So here the here the Lorentz structure of the neutrino interaction is just a scalar compared to vector NSI, where we have here a gamma mu. Okay, so first scalar NSI. So this operator looks like a Yukawa interaction term. So this induces a mass for the neutrinos depending on the fermion density. And this affects the masses which enter our Hamiltonian, which governs neutrino oscillations. The Hamiltonian is shown here. The Hamiltonian depends on the P and S matrix, which brings us from the flavor basis to the mass basis. The neutrino masses themselves, which are encoded in this mass matrix M, plus this matrix V, which has all of the standard model matter potential in it. So if we now have this scalar NSI, we affect this matrix M squared in here in the Hamiltonian, namely this matrix M now gets shifted by a delta M, by a contribution to the mass matrix, and this contribution delta M depends on the strength of the scalar NSI epsilon, and it also depends on the absolute neutrino mass scale M0. So there are some constraints. The best constraints, of course, come from environments which have the highest fermion density, which is the sun. So solar neutrinos provide currently the best constraints on scalar NSI. Vector NSI, on the other hand, lead to new forward scattering interactions with matter. They do not affect the neutrino mass matrix, but this affects the potential the neutrinos feel when they travel through matter, so a new matter effect. So we populate this matrix V, which in the standard model just has an entry in the 1,1 element. That's the charge current interaction of electroneutrinos. But if you have NSI, you can populate this whole matter potential with different NSI flavor combinations. And we parameterize this strength of this new interaction, so this NSI parameters, against such that they are proportional to the fermion matter potential. So it depends again on G Fermi, the matter potential of the Earth rho, as well as the neutrino energy. Right, so all of the neutrinos also have charge current interactions. So we have here of the whole diagonal here has an entry as well, but we can subtract this overall entry from the diagonals because this is just a phase of the Hamiltonian, or in the end, so it doesn't matter. So we already subtracted all of these neutral current interactions of neutrinos in the standard model. Okay. Yes, so for vector NSI again, so this leads to new forward coherent scattering with matter, which is independent of the mediator mass. Unless your mediator has a mass which is of the order of 1 divided by the depth of the neutrinos traveling through the Earth, because then you have a depth-dependent potential. But in general, you do not have a dependence on the mediator mass. And again, the Hamiltonian then looks like this. And to test the NSI parameters, you heavily rely on this matter potential A, which depends again on the energy of the neutrinos and the matter density. The higher the neutrino energy, the longer they travel through matter, which means the higher the density is they encounter, the bigger is the effect of vector NSI, the better are our constraints. So the best way, the best way to test NSI is to go to a long baseline, high energy, high matter density experiment. And this is given by high energy neutrino sources with long baselines, namely atmospheric neutrinos at IceCube. Right. So just coming back here, so we have so as you can see here, we have real diagonal NSI parameters. We have 3 of them, and 3 off-diagonal complex NSI parameters, which we parameterize with an absolute value on the phase. Since we can always subtract 1 term on the diagonal, we actually have, instead of 9 3 parameters, we have only 8 3 parameters which can be probed by oscillations, which are 2 differences of the diagonal NSI parameters, three phases of the off-diagonal NSI parameters, and three absolute values of the off-diagonal NSI parameters. These parameters, which enter here in the Hamiltonian, are related to this NSI parameters of the Lagrangian is this way. So they depend on the average matter density of the fermions you are coupling explicitly to. Okay, so these are the constraints from IceCube, which currently provides the best constraints on NSI. So you see on the left the constraints on the diagonal NSI parameters, on the right the constraints on the three off-diagonal NSI parameters. So you see a couple of different experiments. IceCube is in dark green, but you also see long baseline experiments like MINOS, like Super K. You also see scattering experiments like Coherent. Yes, but in general, IceCube is the experiment which provides currently the strongest constraints. So let's look at these constraints in a little bit more detail. So the strongest constraint is an epsilon mu tau, as you can see here. Why is that? Because it seems kind of challenging. Epsilon mu tau involves a new interaction of tau neutrinos and mu neutrinos. Tau neutrinos are really hard to observe experimentally. They have a large branch, so tau leptons have a large branching ratio into quarks. It's a very messy final state. It's actually really hard to observe tau neutrinos experimentally. So how comes that we have that epsilon mu tau is actually the NSI parameter which is best constrained? The answer is, well, we actually do not have to observe tau neutrinos. Another challenge is also that the number of tau neutrinos we have seen is low. So here is a plot of the number of tau neutrinos we have observed as a function of like the time. You see that right now we are talking about, well, probably like 10 to the 3 tau neutrinos, which we have seen explicitly. That is very few. The magic here is that we do not actually have to observe tau neutrinos. So long baseline and atmospheric neutrino oscillations are dominated by the mass eigenstate nu3, which contains both mu neutrino and tau neutrino. So if we use mu neutrino disappearance data from atmospheric neutrino or long baseline experiments, we are effectively constraining if tau neutrinos have a new interaction. So we do not have to detect the tau neutrinos. The fact that during propagation, which happens as a mass eigenstate nu3, you have a little bit, or actually half of it, is tau neutrino, and the other half is basically mu neutrino. So you do not explicitly have to observe tau neutrinos. You can just use mu neutrino disappearance. You just observe mu neutrinos to constrain epsilon mu tau. We have a huge data set of mu neutrino disappearance data from IceCube as well as from long baseline experiments. The next parameter I want to talk about is epsilon tau tau minus epsilon mu mu. This is a diagonal NSI parameter. This affects the atmospheric mass splitting. So you can just compare the results we get for this atmospheric mass splitting, which is called delta M32 squared, from atmospheric mu neutrino disappearance, again propagating through a very long baseline through the Earth, to measurements of the same parameter from reactor neutrino experiments which are in vacuum. There would be no NSI, no new neutrino interactions. If you see a difference, this would mean that neutrinos, atmospheric neutrinos or long baseline neutrinos have new interactions. We haven't seen that, so epsilon tau tau minus epsilon mu mu is actually relatively well constrained. Sorry. The next two parameters are epsilon e mu and epsilon e tau. Both of them are not constrained, like greatly constrained, and they are like constrained around the same strengths. because for both of them, you want to use electron neutrino appearance from atmospheric neutrinos. Problem is, it's kind of hard to observe electron neutrinos compared to neutrinos. They just have a low yield. If you want to look at electron neutrino disappearance, you don't have a lot of electron neutrinos in atmospheric neutrinos. So this explains why both of these NSI parameters are less constrained than epsilon mu tau. It's just a little bit more challenging. Finally, epsilon EE minus epsilon mu mu is the worst constrained NSI parameter because there are just not that many high energy electron neutrinos. So it's just statistics, which is very challenging here. The other statement is that, as you can see here, you have like this constraint here, this dark green constraint as a block, but then there is also a region of parameter space where epsilon EE is equal to -2, which is allowed at the same confidence level as epsilon EE minus mu mu equal to 0. So there is this degenerate region called the LMA dark solution, which is an exact degeneracy in oscillations, which allows you to flip the neutrino mass ordering in the presence of NSI. And in oscillations, you are not able to distinguish the standard model without NSI from the solution where you have NSI, in particular epsilon EE equal to -2, and a flipped neutrino mass ordering. More on that later on. So yeah, that is just to give you an idea where we currently stand in our constraints of new neutrino interactions called NSI, so new interactions of neutrinos with standard model fermions. In general, order of 10% of the Fermi interaction, new interactions of order 10% of the Fermi interaction are still allowed for neutrinos. That's huge. Okay, so coming back to this LMA dark degeneracy, is actually kind of challenging because this means that in neutrino oscillations, if there is really NSI realized in nature, it is impossible to determine the neutrino mass ordering with oscillation experiments. Determining the neutrino mass ordering, which boils down to the question if the lightest neutrino mass eigenstate has the most amount of electron neutrino, that is the case in the normal ordering, or the lightest mass eigenstate has the least amount of electron neutrino, that's the case in the inverted mass ordering. Which one of them is true? That question is going to be answered with the next generation of neutrino experiment, in particular the Dune experiment. However, they cannot answer this question if this LMA dark degeneracy is realized in nature. They are not going to be able to distinguish these two cases if an epsilon EE is equal to -2. It's an exact degeneracy in all oscillation channels. It's a degeneracy of the Hamiltonian. You cannot do anything intelligent there. It is just an absolute degeneracy. So that is a very interesting region of NSI parameter space and something we can try to target, but not in oscillation experiments. So why do we want to answer this question? Because the neutrino mass ordering has also important implications for other observables. In particular, for neutrinoless double beta decay, where you see on the x-axis the mass scale of neutrinos, the lightest mass. On the y-axis, you see the particle physics observable in neutrinoless double beta decay called m beta beta. And in orange and purple, you see the two theoretically allowed regions, which are different in inverted and in normal ordering. So if you're an experimentalist trying to pursue neutrinoless double beta decay, it really depends on the target you want to set in your experiment. It's really important to know if the inverted or the normal neutrino mass ordering is actually true. It is for neutrinoless double beta decay, if the inverted mass ordering were true, that's better because the allowed region for m beta beta is much larger than in normal mass ordering. But yeah, a similar question also arises for experiments like the Katrin experiment, which aim to measure the absolute neutrino mass scale via beta decay endpoint measurements. Also here, there is a dependence on the lightest mass. Also in cosmology, which aims to measure the sum of the neutrino masses, and the observable Foucault-Rien, they are both larger in inverted ordering than in normal ordering. So your target sensitivity of the experiment you're proposing is different depending on which ordering is actually realized in nature. Okay, so since we have this LMA dark degeneracy in all oscillation channels, we cannot use oscillation experiments to exclude it. So we have to resort to the other way we can test neutrino interactions, which is by using neutrino scattering experiments. So we do that, but in neutrino scattering experiments, there is a dependence on the mediator mass. So there is always a lower bound on the mediator mass which can be probed. Neutrino scattering experiments like NewTEF and CHARM ruled out this LMA dark parameter space for mediators which have a mass more than 10 GeV. To rule out this LMA dark solution for lighter mediators, you need experiments which have a process with a lower momentum transfer. And the ones we have access to was actually observed for the first time a few years ago, and this is called coherent elastic neutrino nucleoscattering, or SEVENS. First observed by the Coherent collaboration a few years back using neutrinos from pion decay at rest. So they have an energy like around like 50 MeV or something. So this allows us to rule out the LMA dark solution for mediator masses above 50 MeV. To go to even lower mediator masses, you need experiments with even lower neutrino energies and lower thresholds, and they are realized, for example, by observing this SEVENS process with reactor neutrinos. Reactor neutrinos have an even lower energy than neutrinos from pion decay at rest, but you need a very, very sensitive detector with a very low threshold to actually observe SEVENS with reactor neutrinos. The momentum transfer is really small. Nevertheless, in 2022, the Dresden 2 collaboration has observed SEVENS with reactor neutrinos for the first time. And in this paper, we analyzed the data and we found that the whole parameter space for the LMA dark solution has been excluded. Now let me explain you why. So here on this plot, you see the mediator mass on the x-axis and the coupling strengths of these mediators to quarks and to electroneutrinos on the y-axis. You see in gray, this is the region which is disfavored by cosmology. If a new mediator couples to quarks and to neutrinos in the early universe, this would impede the free streaming of neutrinos. So this is already excluded, even down to very low coupling strengths of this new mediator. So we only have to exclude a mediator with masses above 3 MeV. Then you see in black, this is this region for the LMA dark solution. It is a band instead of a very thin line, because there's, of course, some experimental uncertainty on where exactly this region is, but the best fit is where epsilon E is equal to -2. And then in different shades of purple, you see the data from the Dresden 2 experiment. The different shades just tell us something about kind of what went into the data analysis. But from what we know so far, no matter what we assume for the data analysis, for these experimental details, this whole LMA dark region, the whole black region, is excluded by this Dresden 2 experiment. Now, this plot is where we assumed equal couplings of this new mediator to up and down quarks. If we break up this assumption, so we allow for the mediator to have different coupling strengths to up and down quarks, there is still a very small region of parameter space allowed. And this is shown here in blue, which is very hard to see, I guess. So these very small slimmers of parameter space are still allowed, but this region of parameter space are going to shrink down even more and more with the upcoming Dune experiment. Yes. So in the end, we, of course, want to completely get rid of this whole basically colored parameter space, in particular, this whole region of parameter space, which is red. Which corresponds to this element dark degeneracy where we are not able to correctly identify the neutrino mass ordering. We only want allowed points in the upper part of the plot, which is green, where we are able to correctly identify the neutrino mass ordering. Yes. Okay. Now, there is a caveat, namely that since the Hamiltonian has this diagonal degeneracy, which means you can subtract an overall factor from the diagonal, you can move the element dark degeneracy from the electron sector into the muon tau sector. So instead of having epsilon EE being equal to -2, you can have epsilon mu mu and epsilon tau tau being equal to +2. And you get the same degeneracy of the Hamiltonian. So you might want to explicitly exclude also element dark in the muon and tau sector, which would require that you have a low energy source of muon and in particular tau neutrinos, and then to like a 7th experiment with them. Now it's non-trivial to actually get a low energy source of tau neutrinos, but boron 8 solar neutrinos arrive at the Earth as muon and tau neutrinos as well as electron neutrinos. And here on the right, I show you a flavor transition probability plot of these boron 8 neutrinos as a function of the energy. And you see that when they arrive at Earth, even though they started out as electron neutrinos inside of the sun, due to this adiabatic flavor transition, when the neutrinos travel through the sun, they exit the sun mainly as mass eigenstate nu2, which has a very large fraction of muon and tau neutrino contained in it, and this is shown here in green. So the neutrinos which arrive on Earth in the peak of the boron 8 flux, they have a very large percentage of muon and tau neutrinos in them, as well as electron neutrinos. So we have this low energy source of muon and tau neutrinos, and we can do 7th experiments with them. In particular, the 7th processes with solar neutrinos. This is a solar neutrino fork, a solar neutrino background at direct detection experiments, which was observed for the first time last summer at Xenon Anton and Panda X with some 2.5 sigma sensitivity. So there is some indication that we observe 7s with solar neutrinos. However, as you can see here in the plot, again, x-axis and y-axis are the same, mass of the new mediator and its coupling to muon and tau neutrinos and quarks. Again, up there in blue and pink, you have the data from Panda X and Xenon Anton. It does not completely exclude the element dark region, which is shown here in gray. But if you increase the exposure to 125 ton years, you can fully exclude the element dark region down to the bound excluded by cosmology. Yeah. So dark matter experiments, dark matter direct detection experiments are actually transforming into neutrino experiments because they now actually see something, but what they see is neutrino events, not dark matter experiments and dark matter signals yet. But they can help us to exclude this element dark degeneracy and hopefully make Dune a big success in determining the neutrino mass ordering. Okay, now let me move on to observing or using the neutral current events we see at oscillation experiments and use them to constrain new neutrino interactions. So this was a paper I did last year together with my collaborators. And what we studied was the NOVA experiment. So the NOVA experiment uses neutrinos from Fermilab and shoots them 810 kilometers to a far detector where it observes them again. Since NOVA wants to see the flavor transition of mainly mu-neutrinos to electroneutrinos to measure the delta CP as well as the other oscillation parameters, it is mainly focused on observing charge current neutrino interactions. However, it also has a lot of neutral current events, and this is what we want to study here. Now, of course, the neutral current channel is actually flavor blind. All of the neutrinos in the standard model have the same cross-section for neutral current interactions. However, if neutrinos now have a new interaction, namely NSI, the scattering cross-section changes in a flavor-dependent way. So imagine, for example, only electroneutrinos have a new interaction. Then the neutral current cross-section is going to be larger than the neutral current cross-section for muon and tau neutrinos. And this is what we want to make use of. Of course, as I said before, the neutrinos do travel a long distance, some 800 kilometers. So they might also experience NSI just in the propagation. So we take both the effects of NSI in propagation and in detection, so in the scattering, into account using a density matrix formalism. And we are particularly interested in new vectorial or axial vector NSI. To do that, because neutrino cross-sections at GeV energies are actually really, really hard, we do a simplification where we say we assume 3 nucleons. And then we just modify the cross-section of neutrino scattering with a free nucleon instead of trying to modify the nuclear cross-section of neutrinos. But we try to model these nuclear effects by multiplying our modified free nucleon cross-section with what comes out of a cross-section generator. So here you see in this plot the neutrino flux and nova in blue, and here you see in different colors the cross-sections. So we at the peak of the nova flux, we have a large contribution to the cross-section coming from quasi-elastic neutral current scattering as well as resonance. At higher energies, we have deep inelastic neutral current scattering. So what we find is that depending on the neutrino reconstructed energy, the number of events we see at the far detector compared to the number of events we see the far detector in the standard model, it can be enhanced by 2 to 3. So we might, in the presence of NSI, we see 2 to 3 times more events at the far detector than without NSI. Now, of course, we also have to take the near detector into account, and because nova has not a huge baseline, not a huge matter density in the end, the results for axial vector and for vector NSI is going to be relatively similar because the sensitivity, as it turns out, mostly comes from the detection, from the scattering of the neutrinos, and less from the propagation of the neutrinos. This is a statement which is true for nova. It is not going to be true for dune, which has a higher energy and a much longer baseline. So to take the near detector into account, we look at the following ratio. So these are the events. So again, that's a function of the reconstructed neutrino energy. And this far to near detector ratio is given by the number of events in the far detector divided by the number of events in the near detector in the presence of NSI divided by the same ratio in the standard model. So it's a kind of a double ratio. And we see that depending on which NSI parameters we switch on, this far to near ratio can change quite a bit, also depending on the energy. So if we switch on epsilon E mu and epsilon mu mu, since at the near detector, we only see the mu-neutrinos we produce, mainly mu-neutrinos at nova coming from pion decays. we only, at the near detector, very close to the neutrino source, we only have mu neutrinos. But at the far detector, most of the mu neutrinos have oscillated away, which explains why this ratio is smaller than 1 for epsilon E mu and epsilon mu mu. This ratio is larger than 1 for epsilon E tau and epsilon tau tau. At the near detector, we do not have any tau neutrinos. In first approximation, we do not produce any tau neutrinos in the source of the neutrinos. We produce only a very, very few D mesons which decay into tau neutrinos and tau charged leptons. We mainly produce really pions and kaons which decay into muons and electrons. However, at the far detector, tau neutrinos appear from mu neutrinos. Mu neutrinos have oscillated into tau neutrinos. So we have a lot of tau neutrinos at the far detector, which explains why this ratio is larger than 1 for epsilon E tau and epsilon tau tau. So without even detecting tau neutrinos, we get sensitivity to epsilon tau tau from neutral current events. This ratio is roughly around 1 for epsilon EE and epsilon mu tau, because either for epsilon mu mu, epsilon EE, you have a very small electron neutrino flux at the near and the far detector. You produce very few electron neutrinos in the source, and the oscillation probability into electron neutrinos is not particularly large. At nova, you have a much larger probability for mu neutrinos going into tau neutrinos. But this explains also why epsilon, the ratio for epsilon mu tau is basically 1, because all of the mu neutrinos you observe at the near detector will have either oscillated into tau neutrinos or the stayed mu neutrinos at the far detector. So this far to near ratio is basically 1 for epsilon mu tau. Okay, so we analyzed the data because NOVA actually has a neutral current data set, which they use to actually observe, to look for sterile neutrinos, which would not interact in the standard model. To look at a neutral current data set at a near and far detector, if you produce sterile neutrinos, then you would observe less neutrino events at the far detector. However, we use the same data set, which corresponds to 13.6 times 10 to the 20 protons on target at the near and far detector for our neutral current study. Now, a problem is, as I said before, the theory prediction for the cross sections suffers from uncertainty on like the flux, on like nuclear physics and everything. So instead of relying on our theory prediction, we fit both at the near and the far detector data simultaneously and use a bin-to-bin fully correlated pull parameters. So what this does is the following. We fit the near detector data perfectly. And then the same pull terms, the same nuisance parameters we use to fit the near detector will then also impact our prediction for the far detector. So we kind of normalize our data such that we have a perfect fit to the near detector, and then we have some prediction for the far detector, and then we can compare to the far detector neutral current data. You see at the near detector, we have like 10 to the 5, 10 to the 6, 10 to the 4, 10 to the 5 events per energy bin. At the far detector, we have much, much less events, but we still have around, 100 events per energy bin. So we still have relatively large statistics at the far detector for NOVA. It will be way more events for upcoming experiments like DUNE. So what was the result of our study? That is shown here. So these are the constraints for vector NSI shown here on the y-axis. The x-axis is just the value of these NSI parameters. We compare in red our constraints to a global fit to all of the oscillation data we have done in this publication here. And you see that the global fit, again, has, because it also takes IceCube data into account, has like a very, very small allowed region for epsilon mu tau, as I explained before. But for some of the NSI parameters, our back of the envelope nova fit, shown in red, is already very competitive with this global fit. In particular, as I said before, the global fit mainly takes oscillation data into account, which suffer from this LMA dark degeneracy. So you have this region here, which can be excluded using our neutral current analysis, which mainly, again, for nova comes from the scattering from the interactions of the neutrinos. But overall, we find complementary constraints from neutral current data compared to charge current data. And at nova, we don't have much sensitivity to the phases of the off-diagonal NSI parameters, but this might very well change looking at different neutrino experiments. More interesting are the results on axial vector NSI, because here the global fit does not take a lot of data sets into account. We do not have a lot of axial vector scattering data. Excuse me. In particular, the dominant experiment in the global fit is the SNOW experiment, which observed or which solved the solar neutrino problem. It observed neutral current scattering of neutrinos on deuterium. However, this particular scattering process is only sensitive to isospin violating axial vector NSI, whereas the NOVA experiment, the scattering on carbon, that's a detector material, is sensitive to isospin conserving axial vector NSI as well. So we find, again in red, our constraints compared to gray, the global fit, stronger constraints for many of the axial vector NSI parameters compared to the previous knowledge. And we also break some of the degeneracies present in the global data set. So for example, everything to the left and everything far to the right. We do not find that these regions are allowed. We only find where the red regions around 0 are allowed from the NOVA data set. So overall, we find novel constraints on isospin conserving axial vector NSI. This is a 2D plot for vector NSI for epsilon mu mu and epsilon tau tau. So the left plot is the expected data, the expected results, and on the right, this is really using NOVA's neutral current data set. And you see that there are some degeneracies as well, if we assume 2 non-zero NSI parameters, but these degeneracies are different from what we can observe in the charge current channel. And here in gray, you see the expected sensitivity using charge current events at Dune. It is smaller because Dune will have much more statistics, but it also suffers from its own degeneracies. Okay, let me finish the last, 3-4 slides going again a step beyond. So far I've talked about neutrino standard model fermion interactions. What about neutrino gauge boson interactions? They arise not at dimension 6, but at dimension 7. So for example, neutrinos could couple to gauge bosons in this way. So they couple to the gauge boson field strength tensor FF or FF dual, F standing for any of the standard model gauge boson fields. And these interactions are not captured in the NSI framework. And as an example, let's look at the effective 2 neutrino 2 photons vertex. So this operator is called the neutrino polarizability operator. So 2 neutrinos coupling to FF dual, suppressed by 3 powers of this high energy scale. So it's a dimension 7 operator, which can be realized via a light pseudo-scalar phi, which has couplings to FF dual as well as to neutrinos. So it could be a Myron, it could be an ALP or something. And in particular, it leads to this new scattering signature of neutrinos. So it's a neutral current. It's a neutral current scattering signature. So you scatter with a nucleus, and you have a photon in the final state. The energy of the photon and the angle of the photon depends on the mass of the mediators and the mass of, the energy of the neutrinos. There are already dedicated searches for this monophoton events in neutral current scatterings and neutrino experiments, because this final state is also predicted in the standard model. So we can benefit from data. And here are the constraints. So the constraints are shown for the mass of this mediator phi and its coupling to neutrinos times the coupling of phi into photons. Right, so it's the product of these two couplings here times this coupling here, which is this product of couplings which shows up in the scattering process. Again, this a mediator with a mass below like 3 MeV is excluded by cosmology. This is shown here in gray. And then you see all of the constraints shown in solid. These are constraints from existing experiments with existing data sets. The strongest constraints right now come from mini boon showing in cyan and the NOMAD experiment shown in red, here for slightly higher mediator masses, just because the NOMAD experiment had a much higher neutrino energy. But we also show experiments, data from, for example, microboon, as well as T2K and Xenon and TON. In the future, these constraints are going to be improved. In particular, the Dune experiment is going to improve these constraints quite a bit, shown here in purple, depending on what, like the running time, 1 year versus 10 years. And this has also been pointed out in this experiment, which has been sanctioned by the Dune collaboration, whereas our experiment, I'm not talking on behalf of Dune. This was just a theory paper. So overall, we find no hint for new neutrino interactions with photons, and the constraints are right now of the order of 10 to the minus 6 inverse GeV on this product of the two couplings, and the constraints will improve by up to 3 orders of magnitude with future experiments. Okay, now let me summarize and conclude. So new neutrino interactions appear naturally in extensions of the standard model with new mediators. New neutrino fermion interactions appear dimension 6. New neutrino gauge boson interactions appear at dimension 7. They can be realized again with like a new neutral gauge boson or a new scalar. NSI, so neutrino fermion interactions, can be tested in oscillation and scattering experiments. There is a complementarity between these two different ways, which can break the degeneracies. I've introduced a new idea to test neutral current NSI using neutral current events at oscillation experiments. In particular, this led to new constraints on isospin conserving axial vector NSI. Currently working on some follow-up experiments, looking at different experiments like Dune, but also improving our treatment, going away from free nucleons. I also talked about new constraints on neutrino interactions with photons. Also there, some follow-up is in the work. Overall, we find that future experiments, in particular liquid argon-based experiments like Dune, like the short baseline program at Fermilab, are the ideal detectors to probe new neutrino interactions, but also theory effort is needed to build consistent models for new neutrino interactions with coupling strengths around 10% of the standard model interaction. Okay, thank you very much. Yes.
So you basically said, well, the standard model isn't the whole story, and so let's extend with just anything that doesn't explicitly violate any symmetry. Are some of these epsilons more motivated than others? Which one are you hoping for is going to be non-zero?
Yeah, that's a very good question. So yes, it is non-trivial to actually build scenarios or models which have relatively large NSI parameters. So the last point is actually kind of crucial. There are two main ways to build this kind of models, which kind of comes back to your question. So one way is Well, the constraints in the tau sector or for the second and third generation are not as strong as for the first generation. So potentially there could be large effects hiding in like epsilon mu tau or epsilon tau tau or something. So these are, I think, from a model building point of view, easier to motivate than new electron-neutrino interactions, which would also affect the electron-neutrino, the electron charged lepton on its own. The other way is you're not coupling directly to the active neutrinos, but you're coupling your mediator to the sterile neutrinos, which then mix with the active neutrinos. So you're running away from like the problems you have due to SU2 invariance. So again, the mixing, the active sterile mixing, which is least constrained, is the mixing of a sterile neutrino with a tau neutrino. So again, there might be, it's easier to motivate larger effects affecting tau neutrinos than affecting electron neutrinos. Mhm.
Where does that order come from? Where you M2 squared is
Yes, that is an excellent question. Yes. So we know that M2 is larger than M1, and M1, sorry, but we do not know yet if M3 is larger than M1 or lighter than M1. So that is kind of the question we want to ask, and it is essentially what distinguishes the two neutrino mass orderings. So why do we know the sign of one of the mass splittings but not the other? We know the sign of delta M21 squared, so the fact that M2 is heavier than M1 from the observation of solar neutrinos. The fact that solar neutrinos, when they get produced as electron neutrinos, and when they travel to the outside of the sun, they have this little bit complicated adiabatic flavor transition. So they transition from a flavor state to a mass eigenstate. And from our observations, it is consistent that the second mass eigenstate, so M2, is actually heavier than the first mass eigenstate, M1. If it were the other way around, our data would look different. We do not have this observation yet for the difference between the mass eigenstates M1 and M3. But this is what Dune and actually currently NOVA and T2K, so the current experiments, aim to measure. To do that, you have to look at neutrino oscillations, neutrino propagation through matter. And depending if your data is more consistent with, well, if M3 is lighter or heavier than M1, you will also automatically answer the question about the normal versus inverted mass ordering. So for this question, M1, M2, the data told us that, solar neutrino data told us that these two masses have to be ordered like this. We do not know about the M1, M3 ordering. But this is going to be solved, hopefully. Yes.
So on slide,
yes.
you see that you said 20%. Does it make with tighter constant or
Yeah. Yes. So you can also look for NSI, just looking at cosmological data. The constraints are around there as well. And there are some studies, I don't think I quote them here on this slide, but the constraints are not much stronger than what I'm currently quoting here. Also, depending on which cosmological data sets you're actually combining, the constraints are typically within like 3 to 5 MeV. They're very, very strong in terms of coupling strengths. But yeah, it's like around there. Yes, I think so, exactly. Slightly tighter, but I mean, it's like, order 1 factor tighter. Right.
So back to the
slide 26.
Yes.
Once we nail down whether the masses are in that order, that would also be a dual measurement that the epsilon B is either very close to 2 or very close to 0. Right?
That is correct, yes. The question is, how do you nail it down? If you nail it down using oscillation experiments, you will always have, let's say, the first equality, right? So you either have no NSI and normal ordering, or you have epsilon EE being equal to -2 and the inverted ordering. But you cannot distinguish these two equalities. So what you would need to do, and it might be very well possible, is using, for example, cosmology. So as you can see here, that if tomorrow cosmology measures the sum of the neutrino mass, and it falls into a region which is consistent with the inverted ordering, let's say here, then if we trust cosmology 100%, we can claim, okay, it has to be the inverted ordering. And then we can kind of trace back. If oscillation experiments also tell us that the inverted ordering is true, then we can exclude that this LMA dark solution. Now, of course, if cosmology measures something which is like neither consistent with the normal nor the inverted ordering, then we are non-divisor, or basically at, well, this point at which I made this plot, which is, you know, a while back, the constraints which we had from cosmology were not discoveries, they were just upper limits right now in the sum of the neutrino mass. So cosmology didn't tell us yet which mass ordering is true, but it could be possible that in a non-oscillation experiment, like cosmology, like maybe the Katrin experiment with the beta decay endpoint, or potentially if neutrinoless double beta decay experiment sees something now up here, which is only consistent with the inverted ordering, then we know, if we trust these experiments, what the ordering is, and then we can infer something about oscillation experiments. Of course, if neutrinoless double beta decay measures something here, which is consistent with both orderings, we are still happy to see neutrinoless double beta decay, but it's not going to tell us, I think, something about the neutrino mass ordering. But yeah, remember that much of this LMA dark region is now excluded. The only point which we want to explicitly exclude is LMA dark in the muon and tau sector, plus this slight slimmers of parameter space if you have not unequal couplings to up and down quarks and electron neutrinos, or up and down quarks and muon and tau neutrinos. Plot looks very similar in this case as well. But I think we are getting there. Yes. Yes, these constraints are mainly from neutrino self interactions, unless because the the supernova modeling is really hard. We don't have very, very good constraints on neutrino electron couplings right now, which are stronger than what I've showed. But we have good constraints on neutrino self interactions, basically. So if the fermions F here are just neutrinos, then you have NSI, like neutrino self interactions. And yeah, there are constraints. And of course, if you're coupling your fermions F, if these are like a lepton doublet, then of course you automatically have interactions of neutrinos with the charged leptons as well as the neutrinos. So it's a model building exercise to avoid maybe the neutrino self interaction constraints, but have the NSI constraints with the charged leptons and the neutrinos. Mm-hmm.
Kind of fit 3-flavor model parameter. Yeah. Does this framework factorize, where you can like, do I have to worry about the NSI parameter and I feel like there's many parameters that need to be very
yeah, so it doesn't really factorize. So you have to You can do fits, and there are some theorists who do this kind of global fits with NSI and without NSI, but you have to, your model has to, input either only standard model or with NSI. You can get around that if you only look at reactor experiments where you don't have meta effects. Yeah, you can do that. The other nice thing, and this global fit people do that. Reactor experiments without meta effect, they are also measuring some of the same parameters as long baseline experiments measure. So if you see a disagreement between the data you are extracting or the observables you are extracting between these two different types of experiments, this might point towards new physics only affecting one of the class of experiments, but not the other. So far, we don't really see that, but the next generation of experiments and the Juno experiment, which already started taking data, reactor experiment combined with like Dune, will make these statements more precise, and maybe we can identify small potential differences.
Well, yeah, we're at
Yes,
5, so I wonder.
sure.
Yeah, I think we have time for more questions in the SPS group. So
Right.
let's thank Julia one more time.
Thanks.